Welcome to The Explainer. Today, we are jumping into the world of machine learning. We're going to break down what it is, how it actually works, and show you why it's become this invisible engine that's powering so much of our modern lives.
So, to get us started, let's think about something you probably deal with every single day, your spam filter. This is one of the oldest and, frankly, most successful uses of machine learning out there, and it's been quietly making all of our lives just a little bit better. But how does it really work?
Well, the old school way was honestly a bit of a nightmare. You'd have a programmer write this huge long list of rules. Like if an email contains the text "for you," then flag it as spam. But then the spammers get clever, right? They start writing "for you" instead. So what do? You have to go back and write another rule. The machine learning approach, though, is completely different. Instead of programming rules, you just show the computer thousands of examples of what spam looks like and what it doesn't. And from that, it learns the patterns all by itself. It's way more flexible, it's more accurate, and best of all, it adapts over time without a programmer having to babysit it constantly.
So here's our game plan for this explainer. We're going to build this thing from the ground up. First, we'll get a solid handle on what machine learning actually is. Then, we'll look at the different ways machines can learn. After that, we'll explore how they take what they've learned and make predictions about brand new things. And finally, we'll cover some of the really common mistakes and pitfalls you need to watch out for.
All right, let's dive right in. At its heart, machine learning kind of flips the whole idea of programming on its head. See, instead of giving a computer a super detailed list of instructions to follow, we're basically teaching it how to come up with the solution on its own.
And this definition from way back in 1959 is still one of the best ones out there. The key phrase, the part that matters most, is without being explicitly programmed. The whole idea is that through experience, by feeding a system tons and tons of training data, we let it figure things out and get better at a task, all by itself.
So, why even bother with machine learning? Well, it's really become our go-to tool for some very specific, very tough kinds of problems. It's fantastic for things that are so complex that we just can't write down the rules, like understanding human speech. It helps us get rid of those clunky, hand-coded systems, and it lets us build software that can actually adapt when things change. And of course, it helps us find those hidden gems, those secret patterns, in huge amounts of data. You might have heard that called data mining.
Okay, now it's important to know that not all machine learning is the same. The biggest way we categorize different styles is by looking at how much human help, or supervision, the machine gets while it's in its training phase.
The two big ones you'll always hear about are supervised and unsupervised learning. Here's an easy way to think about it. In supervised learning, the data you give the machine comes with an answer key. Each email is already marked or labeled as spam or not spam. But in unsupervised learning, there is no answer key. You just give the algorithm this big jumble of data and basically say, here, find the interesting structure in this all on your own. So supervised learning is perfect for tasks like classification, predicting which category something belongs to, or regression, where you're trying to predict a number, like the future price of a car. Meanwhile, unsupervised learning is what you'd use to discover hidden groups in your data through clustering, or to spot really weird, unusual events with something called anomaly detection.
And then there's this third category, reinforcement learning, which is a totally different beast. In this case, you have what's called an agent. Think of a robot or a game-playing AI, and it learns purely by trial and error. It tries something, it gets a reward or maybe a penalty, and it does this millions and millions of times. Over time, it figures out the absolute best strategy or policy to get the most rewards. This is exactly how programs like AlphaGo taught themselves to become the best Go players in the world.
The real magic of machine learning isn't just about how well a model understands the data it was trained on. No, the true goal, the holy grail, is to generalize, to be able to make accurate predictions on new data that it has never, ever seen before.
And there are basically two main strategies for doing this. The first is called instance-based learning, which is kind of like learning by pure memorization. It just stores all the examples it's seen, and when a new one comes in, it just finds the most similar one it remembers. But the second approach, model-based learning, is different. It actually analyzes all the examples to build a general model of how things work, and then it uses that abstract model to make its predictions.
Let's make this a little more concrete with a real-world example of that model-based learning. Let's say we want to figure out if there's a connection between how wealthy a country is and how happy its citizens are.
So we start by getting some data. For a bunch of different countries, we have their GDP per capita and a life satisfaction score. Now, just by glancing at this table, you can probably start to see a trend taking shape, right? It kind of looks like as GDP goes up, so does life satisfaction.
And this brings us right to the core process of model-based learning. It's really a four-step dance. First, you study the data. Then, you select a model. In this case, a simple, straight line or linear model seems like a pretty good guess. Next, you train it. This is the magic part where the algorithm automatically adjusts the model's settings or parameters to get the best possible fit to your data. And finally, you can take your trained model and use it to make predictions on new data. That last step is called inference.
So, whenever a machine learning project hits a wall or goes wrong, it almost always comes down to one of two things. Since the whole process is about picking an algorithm and then feeding it data, the problems naturally fall into two buckets. Either you have a bad algorithm or you have bad data. Let's start with bad data, because honestly, this is usually the bigger issue. Maybe you just don't have enough data to begin with. Or maybe the data you do have isn't a good reflection of the real world, which leads to all sorts of bias. Your data could also just be messy, full of errors and noise. Or, and this is a big one, it might just be missing the key pieces of information the model needs to actually make good predictions.
There's this old saying that is pretty much the golden rule of machine learning: garbage in, garbage out. The quality of your results is completely dependent on the quality of your input data. A huge chunk of any machine learning project is what we call feature engineering, which is really just the art of figuring out what information to actually show the model in the first place.
Now for the bad algorithm problems. This is where we get into a delicate balancing act. On one side, you have overfitting. This happens when your model is so complex that it starts memorizing the random noise in your data instead of learning the actual underlying pattern. And on the other side, you have underfitting, where your model is just too simple to even capture the pattern at all. The goal is to always find that perfect sweet spot, right in the middle.
So one of the main tools we have to fight that overfitting problem is a technique called regularization. The easiest way to think about it is like a dial that you can turn to control the model's complexity. You're essentially putting constraints on it, forcing it to be a little bit simpler. This helps you find that perfect balance between fitting your data well and still being simple enough to generalize to new situations.
The big takeaway here is that there's no single best algorithm that works for everything. There's actually a famous idea called the no free lunch theorem, and it basically says that a model that's amazing at one task might be terrible at another. The only real way to know what works for your specific problem is to try out a few different models and see which one performs the best on your data. So, we've covered the what, the why, and the how of machine learning. We've gone from the different learning styles all the way to the tricky pitfalls like overfitting. With these fundamental concepts, you now have a whole new lens to look at the world with. So the final question isn't just about what machine learning is, but what could you do with it? What problem out there that matters to you could be solved if you just had the right data?